Okay, so let's see what the problem needs. You have a long fence which consists of n sections. Unfortunately, it's not painted, so you decided to hire Q painters to paint it. Ith painter will paint all sections X such that X greater than or equals to Li Ri. So the ith painter will paint the fence starting from Li to Ri. Unfortunately, you are on a tight budget, so you may hire only Q minus 2 painter. Obviously, only painters you hire will do their work. You want to maximize the number of painted sections if you choose Q minus 2 painters optimally. And a section is considered painted if at least one painter paints it. So if there are 3 painters who painted the same section, it's no difference than one painter painted this section. It's the same thing. And we have here n, which is the length of the fence. Is it the length of the fence? Yes, the number of sections. It's the length of the fence is up to 5 times 10 power 3, and q is up to 5 times 10 power 3. Okay. So can someone tell me how can we solve this? Or even if it's a naive idea that will time limit. The easiest idea that you can think of, but that is right. First, did you all understand the problem, the statement? So we will choose, so more formally, we have an array, okay? We have some array of size n, and we have q segments. Each segment is in form LR, like this. We have, for example, let's say we have four segments, so q equals to 4. And the first segment is something like this. The second segment, okay, something like this. The second segment, something like that. The third segment, just like this. And this is the fourth segment. So here the first segment starts at L equals to 1 and R equals to 1, 2, 3, 4, 5, 6. And here 6. And here this starts from 3 and ends at 7, 8, 9, 10. And here we start from 2 and ends at 9. And here it starts from 10 okay, 1, 2, 3, 4. Let's order these to make things easier. 4, 5, 6, 7, 8, 9, 10, 11, 12, 14. Okay, so here's an example of some input. We have n equals to 14. This is the length of our fence. And we have q equals to 4. We have 4 segments. We want to choose only q minus 2 segments.
Sorry, n is equal to 14, right?
Yes.
Okay,
n equals to...
and painters is 4, like 4 painters.
Yes, we have 4 painters.
Okay, sorry, continue.
Okay, no problem. So we have q equals to 4. That means we have 4 painters, and n equals to 14. This is the size of the fence. So we'll have four segments formally. Let's forget about painters and these things. We have 4 segments, okay? Each segment starts from Li, so it covers all the cells starting from Li to Ri. And we want to choose only 2 segments, not only 2 segments. We want to choose only q minus 2 segments. So actually we want to remove 2 segments, okay? We want to choose only k minus 2 segments, so we'll remove 2 segments to maximize, and after removing these two segments, we want to maximize the number of painted cells. Okay. So let's see, for example, here for this example, all the cells will be painted, right? So because all the cells are covered, all these cells are covered with this segment, and all these cells are covered with this segment. All these cells are covered. All these cells are covered. Okay. But we want to remove two segments to maximize the number of painted cells. So I don't know actually which two to remove. So we could remove. Let's think. I think the best to remove. Okay, 1, 2, 3, 4. Here, 1, 2, 3. I think these are the best to remove. I think because if we remove, no, yes, these are the best to remove. I think because if we remove these two, then the painted segments, the painted cells will be this, and then this will not be painted. This will not be painted. This not, and this will be painted. 1, 2, 3, 4. Okay, so we now have three. We have only three unpainted cells. Okay, so actually we want to choose these q minus 2 segments optimally to get the maximum number of painted cells. Okay, any ideas on how to perform this and how to solve this problem?
I think we can
Okay,
remove
say.
first and second. So if we remove first and second,
Oh, yeah, I think you're right. Yeah, okay, that's correct. First and second. Yeah, then look through that. So for first and second, everything will be painted except this cell, right? Okay, so this is the optimal thing. Yeah, this is the optimal solution. So our algorithm or our solution should output here 13, right? Print the maximum number of painted sections. So our solution here for this example should print 13 because the maximum number of painted sections we got here are 13. So anyone have an idea on how to get this maximum, even if it's naive or brute force solution that tries every possible thing? No one has an idea?
I guess we can maintain a set. Can you hear me?
Yeah, can you?
So basically, we can maintain a set and keep on adding the blocks which are covered. For example, if we keep a set S, and for the first one, we'll add the numbers from 1 to 6.
Okay.
Then for the second, we'll add the numbers from 3 to 10. Anyway, set will remove the duplicate, so the covered will be from 1 to 10. Then again, likewise, we'll add for the everything, and we'll get the size. Like, what's the size of the set? Now, for each one, we'll keep on removing and checking the size. So, which gets the best size among the two removed? So that will be the best one to be removed.
Okay, so we will make two nested loops to check which two will be removed, and then try to calculate this set every time, right? So we'll make two nested loops that pass through every pair of segments, and then try to remove this pair, and then check for the rest segments. If we put them to this set, what will be the size, and then get the maximum size. Is this correct?
Yes.
Okay, this is obviously a correct solution, but of course it will time limits because. So first, let's try to calculate the complexity for this solution you're saying. So we have everything is up to 10 power. Let's say 5 times 10 power 3. Okay. So we will make two nested loops to check for every pair of painters. If we try to remove them, what will happen? And at every time in these loops, we will try to calculate the the number of painted cells. And with calculating this with this cell, with this set solution, we will go through every segment. So they are O of n segments, O of q segments. And for every segment, we will take a time of O of n again, because we are, for example, if we are from 2 to 9, we will pass from 2 to 9 and add to the set 2, 3, 4, 5, 6 until 9. So the overall complexity will be O of n power 4 log n. Okay. So the overall complexity for this solution is O of n power 4 log n. And this is correct solution, but it will time limit. Okay. So what we want to do here is not decreasing it by one dimension, but we want to decrease it by 2 dimensions. Okay. So we want to calculate this at a maximum of n squared. Okay. Of n squared or of n squared log n. So let's see how can we decrease this. And of course, if anyone have any ideas to decrease the complexity, you can say. Okay. Let's formalize this thing again and make it easier to. Let's forget about. So let's after putting these segments in this way, let's put them in our array in such a way that makes it easier for us to get the cells. So for this cell, we have one segment covering it, right? Let's increase the size. Okay. Oh. We have one cell covering this. Okay. Let's put lines at the boundaries of every segment. Okay. Okay. So here we have one cell covering it. Here we have actually we have 2 painters covering this cell, and here we have one painter. Here we have 2 painters covering this cell, and here we have 3 painters covering this cell, and here we have 3. Here we have 3. Here we have 3. Right. Here we have 2 painters, and here 2. Here 2, and here 2. 1, 1, 1, 1. Okay, is that clear? So what we just did now is we put at every cell the number of painters that painted this cell. If we of course put all the segments with each other. Okay. So we might let's decrease the complexity that you said now, the solution that you said now, let's decrease its complexity by only one dimension. So we said that this is a solution of O of n power 4 log n. We can decrease the complexity of this solution to O of n power 3 log n. How can we do that? So we can calculate this array, this thing I did here, 1, 2, 3, 3. We can do it on only O of n, not O of n squared. Okay, so I don't have to loop from Li to Ri to just get the number of cells that are in this segment. Okay, I can just make one iteration that calculates this. How can you do that? So after making this, let me say to you the solution that is O of n power 3. We can loop again for every pair of segments, and then try to remove them. So now let's say we had at first q equals to 6, and we are now at inside the loop, and we have only available four painters. So we choose now these 4 painters, and we want to see what are the cells that will be painted using these 4 painters. Okay, so we can calculate this in O of n. So, and I'll say to you now how can we calculate it. So for this solution, after calculating this, to know which cells are in our cells are in our fence painted, we just calculate the number of cells that don't have 0 value. That's it. So this cell don't have 0 value, and this cell don't have 0 value, and all of these cells don't have 0 value. So the answer for this particular set of segments will be 14, right? 14. So now we can calculate, after calculating this thing, and I'll say to you how, we can get the solution in O of n power 3 only, right? So we can make nested loop and try removing every possible pair, and at every iteration we try to
Sorry, how we
calculate
are arriving at 14? Can you come again?
how. Okay, so the number of cells are 14 cells, right? And we have
Yes.
exactly 14 cells that are covered. So each every cell here are covered. Okay, so the answer is 14.
Okay.
If initially we had q equals to 6, and we are still now here at 6 minus 2, which are 4 sets, and these are the segments we're in. Okay, so now let's see how can you calculate this array in one iteration only, and then see which cells are not 0. So let's remove everything. And see how can you calculate that. So to calculate this, let us take segments one by one, and then when we are taking one segment, so for example, we are taking, this is the first segment we are taking, we will add one at its left endpoint and remove one after its right endpoint. We just, so initially everything is 0 here in this array. Okay, everything is 0. So we'll add one in its first point and remove one at its endpoint. After its endpoint. Why we are doing that? Because we can just calculate each cell that is covered from this set by iterating from the first cell in the array and going to the end, and just adding for each cell the cell before me. So that means here I added one. So for this cell, to know if it's covered or not, I'll add the cell before me. So this cell I'll add one. Okay, and this is 0, I'll add one, and here I'll add one, here I'll add one, here I'll add one, and here I'll add one, right? So it will be 0. So now I know that this these cells are covered by some painter. Okay, but again, what is the benefit of doing that? We could have just looped from 1 to 6 and knew that. No, but when we do this for multiple segments, we can do one iteration and calculate this. So we can here add one here and remove one here, add one here and remove one here. Okay, but let's, to make things easier, let's make it with only 2 segments. Okay, just to make things clear. Okay, so I added one here and removed one, and added one here and removed one here. So now let's iterate from the first cell. Let's go from the first cell in our array, and then add one for each cell. I'll make the value of this cell plus equals to the value of my previous cell. Okay, so for this cell it will be 1, and for this cell I'll add 1, right? So it will be 2. For this I'll add 2, the previous cell, 2 and 2 and 2, and here it will just be 1. Okay. So here it should just be 1, and here 1, here 1, and here 1, and here -1 plus 1 is 0. Okay, so did you get this? So this is the most important part in our solution. So when you have multiple segments, we'll just keep adding. We'll add one in its beginning and remove one after its end. And then if we have n segments, so many segments, and just we added one at their beginnings and removed one after the endings, then we could just go through the array from its beginning to its end and keep getting the value and keep adding the value of my previous cell. And that way we got the number of cells painted in our fence. So now here let's double check. So we have here one cell, that's right, one cell. Actually one painter, that's right, one painter. And starting from here to here, we have two painters, that's right. And starting from here to here, we have one painter, and that's also right. Okay, so do you understand what we did here? Everything's clear? No questions? Okay, so after doing that, we can actually decrease the complexity from O of n power 4 to O of n power 3. We can loop through every pair of segments and just dismiss them, discard them, and then add the other segments with this way I said here. So I removed the log and I removed the n. So I made the complexity of n cubed exactly. Okay, but it's still not enough. So we make more we may need more complex solution. So we want to make it O of n power 2. Okay, so let's first to not to make a high jump, let's code this easier solution to make things clear what we're doing here. Okay, and then we'll edit it to make it O of n squared. So now we said that the answer will be coding is O of n cubed. First we'll take n and q. And then I want to make a bunch of arrays here. So this array, let me call it fence. Okay, let me call this array fence. And initially, and let me do it not of size n, but instead of size n plus 2. Why? Because I want it to start from 1 and to end at 1. But also I want to have an extra I want to have an extra cell at the end and an extra cell at the beginning. Why? Because I'm decreasing 1 at the end after the end of each segment. So when it happens that I have a segment that ends at the last cell, then I'll be decreasing 1 in this empty cell. It will not make any difference in our solution, but not to get array out of bounds errors and something. Okay, and for this extra cell, it will have an index 0, but we want everything to start from 1. It will make it easier for our solution because we have a bunch of arrays. Okay, so we have f of n plus 1 initially to be equals to 0. What else we have? And we'll have the array that stores the L of I and R of I's, the L's and R's of our painters, right? So it will be pair. So for those of you who don't know C++, pair is just a container that takes, so pair takes just two int at a time. So we can make pair of string int, car int, anything. Okay, so pair int. It will be an array. So let's painters, and it will be of size q. Okay. Okay. Let's take the input. No, not n, it's q. I equals 0. I'm taking li's and ri's, right? Thank you. Painters of I dot first. So first represent the first element in the pair, and then Painters I. Wait a second. Let's make this painter. Or actually, to make things easier in the code, let's make this P. Okay. So now that we took the painters, I want to make another thing. We want to add one at the beginning of each L and remove one after the ending of each R. Okay. So to make things easier, we'll take int L R sim L R. Okay. And f of L plus plus f of R plus 1 minus minus. So I remove one after the ending and add one at the beginning. Okay, and of course pi equals L no. So that means that the first element in the pair is L, the second element is R. That's it. Okay. So now we want to go one iteration from I equals to 1 until n, and then calculate the values for the cells. So int I equals to 1 I plus plus I plus equals f minus 1. That's it. Okay. Let's test this for something else. So say f of I to show you that everything works fine. So let's try our example here, okay? How can I redo? Yeah. Okay, so let me here remove 1, 2, 2, 2, 2, 1. Okay, so here I'll give our program this example. N is from 1 to 14, and these segments, and we'll see will it output the same array as we made here or not. Okay. So I'm outputting every f of I from 1 to 14 after making that. Of course, these are zeros. Okay, let's see. So n is 14. And q is 2. And we have 1, 6 and 3, 10. Is it 10? Yeah. 1, 6, 3, 10. It should, oh yeah, we didn't put the number of test cases. 14, 2, 1, 6, 3, 10. Okay, so it's correct. 1, 1, 2, 2, 2, 2, 1, 1. Here we are starting from 1, okay? 1, 1, 2, 2, 2, 2, 2. 4 twos and then 4 ones. Okay, everything is correct here. So now we calculated the number, we calculated in O of n only the number of painted cells. Okay. Okay, so let's make our nested loop to try to discard every pair in Q of painters. Okay. So for int j equals to I plus 1, which is more than qj plus plus. Actually, this is until q minus 1. Okay. So now we are standing at painter number I and painter number j, and we want to get rid of them. Okay, we want to remove them. and try to see what will be the number of painted cells here. Okay, and of course we'll have answer equals 0 at first. So let's try to calculate. So now we will calculate all of this again here. Okay, so remove it here. I'm just showing you. Okay, so I'll here loop again for each painter except I and J to add them to our fence. Okay, so for int k equals to 0, k is more than q, k plus plus. If k not equal I and k not equals to j, then I'll add this painter, I'll make it paint the fence. Okay, so f of p of k dot first, which is the left point, make it plus plus, and f of p of k dot second plus 1 minus minus. Okay, I don't need these brackets. Okay. So now I made 3 nested loops. Okay, so the overall complexity is of n power 3. But what's the answer? So we want to calculate the answer, and we will calculate it inside this second nested loop. Okay. So after adding the values for the fence, okay. After adding the values for the fence, we want to go all over the fence again and check which cells are painted. Okay. So int cells equals to 0. So int r equals 1 or smaller than equal. Is someone sorry, let me check something. You can hear me right now, right? Okay, I think yes.
Yes.
Okay, let's continue.
Yes.
Okay, thanks. So we're going from I up to N. Can you please, if you're not talking, mute yourself? Okay, to make. Okay, thanks. So now cells I plus equals to cells. So what I'll do here is that if f of I not equals to 0, of course. So if it's greater than 0, then cells plus plus. Okay. So if I found that f of I here, not I, we want to make it k. So if f of k is greater than 0, then this cell is painted. Okay. But actually, after adding 1 and removing 1, I want to calculate the values for each cell, right? So I'll make another loop here. So int k equals to 0, k small, int k equals to 1, k smaller than or equals to n, k plus plus. F of k plus equals f of k minus 1. That's it. Okay. So I'm adding 1 to cells. What is wrong with cells here? Okay. So I'm adding 1 to cells if f of k is greater than 0. And this is the same as cells plus equals f of k not equals to 0. That's nature. Okay, so after that, I have the number of cells that are painted now. So I want to maximize this number with our answer. Okay, I want to take the maximum out of all of these choices. So answer equals to maximum answer for cells. And then at the end, I print answer. Is everything clear in this solution of n cubed? Everything clear what we are doing here? Because I won't go to the next step unless everything is clear.
Just one question, like why we are taking from I equal to 0 to q minus 1, 22
Yeah,
line.
okay, I thought you would ask about that. So now we are looping through every pairs, right?
Yes.
So I could make from I equals to 0 until q, and then from j equals to I plus 1 until q, because I I want to take j after I because I've passed at everything before I. But for I, the last pair, so for the last pair, I will not go to the last element because for the last pair, it will be something I will be here and j will be here. So I will not reach q because, for example, if I have 4 elements, so A, B, C, D, and I want to loop through every pair. So I'll take A with B, and then A with C, and A with D, right? And then B with C, B with D, and then C with D, right? So I will not go after Q minus 1, okay?
Okay.
So that's it. So any other question in this solution? Anything is not clear? Okay, let us test it with these small examples. So it should work here with every example because everything is small, right? Let me double check is everything okay or not. And actually, I don't need to, just to make the code easier, I don't need to make this second loop. I calculate everything here. Okay. Okay, let us try. Is there something wrong? Oh, so it needs, so there is no T here. Hmm. Okay. 7. And the answer is 7. So it outputted 4 and the answer is 2. 1, 2, 2, 3, 4. Okay, there is some bug here. Let me check it. it's also 4. So there's something wrong here. So this program checks every cell, and it's not discarding anything. I got it. So we are not resetting. So we should reset the fence array to be 0 each and every time in our nested loop, right? Because we are recalculating everything again. So after finishing, we'll just reset, not here, but before starting, we want to set f to be 0. Size of f. That's it. Okay, it's correct now. Should be 3. Okay. Okay, everything is clear now for this solution before moving on to the solution that removes one dimension, because it will be harder than this. So everything's clear? No questions? Okay. Let's move on to our example and see how we could fasten this. Okay. So instead of checking for every pair, why not do something else? So let's say, let's erase these segments. Okay. Actually, I'll remove everything. Okay. So now we have these 4 segments. Okay. Let's put the numbers corresponding to the number of cells. 2, 3, 3. Let's move these lines because they are distracting. 2, 3, 3, 3. Okay. So my solution to removing one dimension, we could pre-calculate some things and don't need to recalculate everything from the beginning here. So we could go just through every pair and then make some constant operation, some O(1) operation, to see what are the number of cells, what's the number of cells that will be painted if we removed I and J. Okay, so we'll try to remove this third loop here that's calculating everything. We'll have some arrays that are pre-calculating some things. So let's see. Let's see what happens if we removed this segment and this segment. What we'll observe here is that the segments that we will remove will only affect the cells that are painted, that have numbers 1 only, right? because this segment and this segment will only affect the cells that have only numbers 1, because if a cell have number 2, then it is painted by another segment, so it doesn't matter if I remove this segment or not from this cell. Okay, so by removing this and this, only the segments numbered 1, only the cells numbered 1 will be removed, right? So for this example, we'll remove the one cells. We will count the number of 1 cells that are inside these 2 segments. All right. But what if we have 2 intersecting segments that we want to remove, uh, like this and this, this and this. So what if we want to remove these 2 segments? At first, we will remove the cells that have numbers 1 inside these segments. Okay, so this cell will be removed. Do we have another one here? No. Do we have another one here? No. But are we finished? So let's this is not a relative example. Let's remove this. Okay. 1, 2, 2, 2, 2, 1, 1, 1, 2. Okay. So now we said that we want to remove these 2 segments. So we'll remove everyone's that are inside these 2 segments. Okay. So we'll check for the first segment first. Uh, then we'll remove this first one, and then this second one. Is there any other ones in this segment? No. Then we'll see the second segment, and we'll check for the number of ones. Here we have this one, here we have this one, here we have this one. So actually we removed how many cells? 1, 2, 3, 4, 5. We removed 5 cells. These are many cells to remove, and what we want to do is, but before saying that, I want to say, are we finished? No, because I have these cells that want to be removed too, but they are 2. Yes, I know, but they are 2, but they are at these 2 segments. So these cells are an intersection of these 2 segments. So if I have any one between these 2 segments, I remove it. And if I have any 2 that is in an intersection between these 2 segments, I want to remove it, then I remove it also, right? So I remove these 2, and these 2, this 2, and this 2. Why I'm removing these 2's? Because they are in an intersection between these 2 segments. So I know that they are not in an intersection in other segments, because they are not 3. If they if there were any segment that intersects at this cell, then this would be 3, for example. Okay. So what I'll do is choose some pair of painters and try to count in an optimal way the number of ones that are between the boundaries of these 2 segments. And then, so I'll try to count the number of ones between the boundaries of every segment simultaneously. Okay, so the number of ones here and number of ones here, and then try to count the number of 2's between their intersection, and the answer for this pair will be the number that I got removed. Okay, so I want to, so what I will do here, what I'll do here then is I'll initially count the number of cells that are painted using all the painters. Okay, then loop through every pair and try to minimize the number of removed cells. Okay, so I try to minimize the number of removed cells because I want to maximize the number of painted cells. Then I loop through every pair and try to minimize the number of removed cells. Okay, so after removing these two segments, then I remove all these cells, and these are too many. Okay, so the answer will be here 4. um, Everything is clear now. Do you all understand what we are doing here and why we are counting this? Any question? Okay,
Can you please repeat again?
okay, no problem. Is there any point you want me to stress in it you don't understand, or everything totally you don't get it?
Oh no, like why we are removing twos? Because once we are removing, and after that intersection of twos also.
Okay, so do you get why we are removing ones or not?
Yeah, because yeah, I got that one. Once we are removing, after that,
Okay, so now we are removing ones because I am sure that if I removed someone in some segment, then I'm sure that there is no other intersection between any other segment at this cell, right? Because if
mm,
there was the other intersection, then it wouldn't be one.
yes,
So this is why we removed one. But what about two? We don't remove any two. We will remove a two if and only if it's between the intersection of these two segments we are removing. So we chose these segments, right? So what are their intersection? So their intersection is this part. So we remove each and every two in this uh, in this intersection. Okay. So if we had, for example, another segment here, then this would be three and this would be three. So we remove only these twos, right? Because I am sure that if I found two between an intersection of two segments, then I am sure that there is no other segment intersecting at this cell because it wouldn't be two, it would be greater than two. Did you get that or not?
yeah, I got it. Thank you.
Okay, all right. So that's what we're doing here. And I want to count. So what is left here is that I want to count the number of ones and twos efficiently as fast as possible. So I want to make a constant operation to count the number of ones and twos at each segment. So I want to call, for example, uh, one. So I want to call, for example, ones li l of r, and it will be equals to some value. Okay, so I want to make this as efficient as possible. And again, I want to make twos. I want to count twos l and r and store in it some other value. So if I could pre-calculate ones of L and R and twos of L and R for every L and every R, then I could easily count the number of ones and number of Y's in O of 1. So our solution will be O of n squared 1. Okay, so let's see how can we, and actually we can calculate this with the same approach we did for calculating the fence. So let's remove everything here and see. So we want to make two arrays that are called ones. Okay, let me first. Hmm. Actually, we don't need to count the number of ones and the number of twos in a 2D array. We can only make it in a 1D array. Why? Because I think you know the prefix sum arrays. So if I have number of ones of R and I want to get the number of ones of L, oh, okay. So ones between L and R will be equals to ones from 0 to R. Uh, okay, I write here better. So if I calculated a prefix sum array that calculates the number of ones from 0 to I, then ones between L and R will be equals to ones of R minus ones of L minus 1. Is that clear? So we can do prefix sums. So ones, so the ones array stores the number ones of I equals to the number of ones from 0 to I, or from 1 to I. Okay, so to count the number of zeros, the number of ones from L to R, then it will be ones of R minus ones of L minus 1. It's just a prefix sums array. Okay, so I can calculate this using prefix sum array. So I'll make ones of n, and it will be size n plus 2, I think. No, n plus 1, because I don't want this extra cell at the end. Okay, I'm not accessing any extra cell at the end. And 2's of n plus 1. That's it. Okay, then I want to make one iteration to calculate the numbers for the number of painters for each cell at the beginning. Before going through anything, I want to count this, and then loop through pairs and try to remove. Okay, so if I enter equals 1, f of I plus equals to f of I minus 1, but I didn't add anything to f here, so I'll make f of L plus plus f of R plus 1 minus minus. Okay, so now I want to calculate the values for ones and twos, and I said now that it's only a prefix sum array. Okay, so I'll just, while I'm going through the fence, I'll just calculate ones and twos. That's it. So I'll only add 1 to ones of I if f of I equals to 1. Okay, so if f of I equals to 1, then I'll just add 1. If f of I equals to 1, then ones of I equals to 1. Initially, everything will be equals to 0, of course. And here, fence will be equals to 0. So if f of I equals to 1, then ones at I equals to 1. But this is a prefix sum array, remember. So at the end, I'm making ones I plus equals ones I minus 1. Okay. And also, I'm saying that if f of I equals to 2, then 2's of I plus equal 2's of I minus 1. And also at the end, I'm saying that 2's of I plus equal 2's I minus 1. But to make the code shorter, I'll just make this in just 2 lines. It's the same thing. So ones of I will be equals to f of I equals to 1. So if it equals to 1, it will be 1 plus ones of I minus 1. And 2's of I equals f of I equals to 2. So this returns a boolean, right? So if it equals to 1, then this value will be 1. And this equals to 2, then this whole value will be equals to 1 also, because it's a boolean. Plus 2's of I minus 1. Okay, so now I finished calculating the values for ones and twos. Let's now loop through every pair of painters and try to remove them and get the minimum removal. Okay, so so now we are standing, we want to remove the painter number I and the painter number J. So what we'll do now is count the number of ones between I and count the number of ones between L of I and R of I, and the number of ones between L of J and R of J. Okay, so int current will be the number of cells that we'll remove. Okay, remove. remove equals 0, or let's just make it remove. So remove plus equals, I'll add to remove. Let's make some variables to make things easier. So I'll make remove equals 0, and I'll have L and R, and another L and another R. So L and R represents the interval for the first pointer, and L and R represents the interval for the second pointer. Okay, let's say L equals to P of I the first, R equals P of I the second. Okay, so now I'll add to remove the number of ones between L and R and L capital and R capital. So remove plus equals to ones of R minus ones of L minus 1. And then I'll add again ones of R minus ones of L minus 1. Okay, so now I removed ones, okay, but I want to remove the twos. So first I want to check if there is an intersection, because if there is no intersection, like for example this segment and this segment, then I will not remove any two. Okay, so I want to check if there is an intersection, then I'll remove any two between the intersection. So how to check if there is an intersection? I'll check if the left end point of the second cell is smaller than the right end point of the first cell. So if the left here is smaller than the right here, then it's clear that there is an intersection. But to make things easier and not make lots of ifs, we will fix that L and R. So we'll try to assume, not try, we will make and fix that L and R represents the interval that's before the interval that's starting at L and R. So that means that this interval, we'll make it always this will represent L small and R small will represent this interval, and L capital and R capital will represent the interval that's after this interval. So that means if L and R are yeah. So that means if L capital and R capital is the interval before that interval L small and R small, we will swap everything. Okay, just to make sure that the interval, the first interval, so the interval before the second interval will be at L small and R small. Okay, so so what we'll check here, see if L capital is smaller than L small. So if L capital is smaller, is that what I want? No. So if R capital is smaller than R small, so that means if I have this R capital smaller than R small, that means I'll swap everything. Okay, just to make sure that the R capital is greater than R small. Okay. If R capital is smaller than R small, then swap R with R. And swap L with L. Okay. Let's just make this here before calculating anything. So now we are sure that R capital, so after making this, we are sure that R capital is always greater than or equals to R small. Okay. So that means that we'll just need to check once. If R small is greater than or equals to L capital, then there is an intersection. So if R small is greater than or equals to L capital, then I know that there is an intersection. And if not, so if R small is smaller than L capital, then there is no intersection. Okay. So the answer for this will be the interval between R small and L capital, right? So I'll remove plus equal the 2's at between R small and L capital. So 2's R minus 2's L capital minus 1. But here is some corner case. 2's minus 1, not here. But there is some corner case that we didn't consider. And it is when we have L capital, not L capital. Yeah, when we have L capital smaller than L small. So we now checked, we now made sure that R capital is greater than R small, right? But we didn't make sure that L capital is greater than L small. So we might have that L capital is smaller than L small. So when we calculate this, 2's R minus 2's L minus 1, we are making this 2's R, we are making 2's R minus 2's L minus 1, so we're counting this interval. But we want to take only this, right? So we'll take, so the left endpoint of our intersection will be the maximum between L small and L capital. Did you get it? It will be the maximum between L capital and L small. Okay, everything's clear. Yeah, and that's it. So now I calculated the removed cells. So now I want to update the answer. So the answer is 0. Actually, the answer should be here increased. So answer plus equals f of I not equals to 0. So if f of I not equals to 0, then I'll add 1 to the answer. And here, when I removed, then answer will be equals to maximum. I'll not make this. So this is our initial sum, okay? Let's call this sum. So our initial sum is all the cells, right? And our initial removed, let's make it to big value. Our initial removed will be big value and I'll minimize it, okay? So removed, I'll take the minimum removed cells and then removed, I'll just remove the removed, okay? So rem equals minimum between rem and remove. So at the end, sum have the sum of all the cells and rem equals to the minimum cells removed. So the answer that we should output is sum minus rem. Sum minus removed. Okay. Okay, everything is clear. Any part you didn't get, especially these parts, they might be confusing. Okay, ask me if any point you didn't get. Let's try. 7. Hopefully there are no bugs. Okay. Okay, 3. Oh, what did it do? Okay. Let's double check if anything's not in place. Okay, let's submit. Oh, what about the first problem? Oh, it's thank you. So code forces, I think this day and yesterday um, had a problem of long queue, so the problems aren't being judged these days, but hopefully this will be solved today or something. Okay, so apparently they will still in queue. So I didn't realize that, but you might. I'll send you the codes now, and hopefully everything works great. Okay, let's get the code. And here the code. So I sent in the chat the codes for these two problems in order. Okay. Any questions before I leave? We finished today, so we solved these two problems. Everything is okay with these problems? Anything you didn't get? Or everything is clear? Why no one's talking? Okay. So any question before I leave? Okay, thank you everyone. I'll see you the next week or something.
Thank you.
Okay. Thank you. Bye.